Hello everyone. In this video, I will be answering a request to talk about logic gates, and I completely understand the request. This is an area that many students find difficult. However, I'm hoping that by the end of the video, once we go through these concepts, you'll find it much easier to approach the questions based on this topic. All right, so let's begin. The first question we have to ask ourselves is, what are logic gates? The easiest way to put it is that logic gates are high-speed switches that either allow current to flow through a circuit or it stops it from flowing through a circuit. As a result, these digital systems or electronic components can exist in one of two logic states. That component could exist in a state of 1 or 0. Well, what does the 1 or 0 represent? Well, the 1 represents true, which means that the circuit and the component is at a high voltage state. And as a result of this, the circuit will act as if it is turned on. Zero represents false, which means that the circuit is at a low voltage state. And is therefore acting as if it has been turned off. All right. For the purposes of Csec, you will be asked to know the 5 basic types of logic gates. And that's what we will talk about next. The first logic gate that we will be introduced to, there's no specific order for them, by the way, is the NOT gate. The symbol for the NOT gate is as follows. I'm going in, arrowhead, circle at the tip, and a line going out. We can annotate this drawing to say what these lines represent. This first line here represents the input state or the input signal. And this line right here represents the output state or signal. Here's something we must appreciate about logic gates. They take an input state or signal and they process it and turn it into one single output state. The NOT gate has only one input state. In fact, it is the only gate that has just one for the 5 that we will discuss. To know the possible combinations and the outcome of the output state, we're going to have to construct something known as a truth table. To know how many possibilities are in that truth table, we will use a formula. I'll just write here the number of possible combinations, and that is based on the formula 2 to the power of n, where n represents the number of inputs. All right. In the case of the NOT gate, the n would be 1 because we only have one input, and so we would only have 2 possible combinations. All right, so let's go about drawing our truth table. Let me see if I can insert it here. All right. So the truth table is, as its name suggests, a table that tells us the truth about the output state. So in this table, in one of the columns here, I'll be putting input. And here I'll be putting output. Right. In the case of the NOT gate, we only have two possible combinations. So I'm going to put those states that are possible, just the 0 and the 1. All right, here's where we understand what the gate does. The NOT gate says whatever the input signal is, or the input state, turn it into the opposite of itself. And that is why the NOT gate is very often referred to as a reversing gate or a switching gate, because it's simply going to switch the state of the input state. So what's the output in this case? If it's 0 here, then it's not going to be 0, it's going to be 1. If it's 1 here, it's not going to be 1 in the output, it's going to be 0. All right, and that's a truth table that we would have for the NOT gate. The second gate that we will look at is the AND gate. Remember, there's no particular order to these. All right, how I remember what the symbol for the AND gate looks like is that I think about the D here. Let me change the color of the ink. Right. I think about the letter D, start off with it, and I simply come out with the lines. So what's happening here? Oops, what's going on with my ink? Right. What's going on here is that we have one input state here, another one right here. And we have an output here. What does this mean? It means that the AND gate will be taking two inputs, processing it, and turning it into one output. We can represent what the possible outputs are in a truth table once again. Before we construct our truth table, we have to know the possible combinations, and that is given by the formula we mentioned earlier, 2 to the power of n. This time, n is going to be 2 because we have two possibilities. So that would be 2 times 2, which is 4. All right, let's insert our table. I think this time we actually have to use a larger table. All right. So I had to have 3 columns this time because we have 2 input signals. So let's label this label here. We have 1 input here. You can call it A. We have another input here. You can call it B. And we have the output. So we have 4 possible combinations this time. That's 4 possible combinations of the 1 state and the 0 state, and even numbers of both. So we can start off by alternating the 0s and 1s. So 2 0s, 2 1s. Then we have a 0, a 1, a 0, a 1. What we're doing here is that we're going to evaluate these 2 inputs to see what the output will be. To know that, we have to understand that an AND gate will only input a 1 if both input states are also 1. In other words, if both input states are at a high voltage state, then the output is also going to be at a high voltage state. For everything else, it's a low voltage or a zero. As a result of that, we can clearly see here that this would be 0, 0 and 1 would also be 0, 1 and 0 would also be 0. And the only time we have the two inputs being 1 is where we have an output of 1 as the outcome. All right. Let's look on the third logic gate that we will see. And that logic gate is called the OR gate. I hope you can realize that the names for these logic gates actually tell us what the output should be. So with the OR gates, the symbol for it is kind of based around its name. I'll just go ahead and do that here. Sometimes the tip of it is sharp, sometimes it's like this. It kind of looks like a spaceship, and it's going to have the two input lines coming out and an output line here. All right, so just like how we did for the others, we are going to make a truth table for this. Let me copy the table. I'm going to make a truth table for this. Let me put it here. Once again, to construct our truth table, we have to know how many possible combinations we have, and that is given by the formula 2 to the power of n. We have two input states here, so it's going to be 2 times 2 once more. We have 4 possibilities. All right, let's go ahead and insert another table once more. All right, so we have one input here, call it A again, another one here, call it B, and then we have the output. Once again, because we have 4 possibilities, we can alternate them. As such, start with 2 zeros, and then 2 1, and then 0 1 0 1. All right, so let's look at what happens here for the OR gate. The OR gate says if either one of these two inputs is a 1, then the output is going to be a 1. So if we have a 1 in any one of these, then it's going to output 1. And that means, let's look at them. 0 0, neither is a 1, so the output has to be 0. 0 1, we have a 1 here, so the output is 1. 1 0, we have a 1 present, so the output is 1. 1 1, again, we have a 1 present, so the output is 1. And there we go. We have the first 3 logic gates that we need to know and their corresponding truth tables. The other 2 logic gates are combinations of, the first one is a NOR that we'll look at. And I bet you can tell NOR is a combination of a NOT and an OR gate. The symbol for this is just a combination as well. So do you remember what the symbol for a OR gate would be? So it looks like a spaceship. The only difference between the OR gate and the NOR gate is that at this tip here, we place a circle. And this circle comes from the NOT gate. So that's the only difference. That's how we represent it. All right, now for the truth table. How is the truth table different? Let me go ahead and insert another table again. How is the truth table different this time? Right. We're going to have input again, A, input, B, and the output. All right. So because of the NOT, it is saying that the NOR gate is the opposite of the OR gate. What happened in the OR gate before? With the OR gate, what we saw was that if any one of the input signals is a 1, then the output is going to be a 1. What that means is that the opposite is true of this. Anytime there is a 1 in the input, it's going to output as 0. And the only time it is going to output a 1 is if there is no 1 in the input at all. All right, so let's write down our combinations. Again, we know that this takes 2 input states. So we have 4 combinations based on the formula that we mentioned before. And we'll write it out as 0, 0, 1, 1, 0, 1, 0, 1. All right. So remember, this is the opposite of an OR gate. What do we have here? 0, 0. We don't have a 1 present. It's the opposite of the OR. So it's going to output a 1. So remember, if we say a 1, it's going to output a 0. That's all. Say the 1, 0. Say a 1, 0. And that's it. That's what the NOR gate is. The final logic gate that we have to know is a combination of the NOT and the AND. This is a NAND gate. Names for these are pretty funny. So it's a combination of NOT and AND. So we just have to remind ourselves of what the symbol for the AND gate would be. And we remember that, we think about the D in AND. Start with a D, bring these lines up. Forgive the squiggly lines again. I feel like I'll be saying this in every video. Anyways, what's the difference? I think you would have guessed it. The only difference between the AND gate and the NAND gate in diagram is that right here at the beginning, we're going to have that circle that comes from the NOT, right? And that represents the symbol that we'll see for the NAND gate. We are going to draw the truth table for this NAND gate as well. Let me insert that. Right? So once again, we're going to have 2 inputs, as we can see. We're going to call them input A and input B. And we have 1 output. All right, we remember how this goes. We know that we're going to have 2 to the power of 2 to tell us the number of combinations. We're going to have 4, and so we alternate that 4. We're going to start with 0 again, 0, 0, 1, 1, 0, 1, 0, 1. And we will begin to look at what the output will be. I want you to think about how that combination of NOT and AND will affect the possible output that we will be getting here. You might have arrived at the answer, and if you have, then that's wonderful. What happens here is that the NAND gate is the opposite of the AND gate. With the AND gate that we saw before, it would only output a 1 if both input states were 1. What this means is that the opposite will happen here. If we see two ones, it's going to output a 0 for the NAND gate. And let's start right here as a result of that. This is the only place you'll see these two ones. So anywhere else we'll get a 1. And that's it. I think this topic is a lot less difficult than it might appear to be if we take it simply, if we don't SWOT. As my students would tell you that I say very often, swatting can be the enemy. You need to have a deep understanding of the topic you're studying, and once you have that, you will be able to complete any question you are given. I hope this has been helpful. You can go through the video, and if there is anything that is of concern to you, then you can run it by me and I'll see how best I can help. I do wish you all the best, and I'm here if you need me. All right, take care.